Molecular polarity refers to the uneven distribution of molecular charge. Molecular polarity is determined by the polarity of each bond and the geometry of the molecule. Two theories describe the chemical geometries and shapes of molecules. The first theory is VSEPR theory. VSEPR stands for valence shell electron pair repulsion. VSEPR theory states that repulsion between the sets of valence shell electrons surrounding an atom causes these sets to be orientated as far apart as possible. The central atom of a molecule can be represented by A, and the atoms bonded to the central atom be represented by B. A BEF to molecule is an example of an AB to molecule, which is linear. An OV to E molecule shows that the central atom A has two bonded atoms B and one lone pair of electrons E. An ammonia molecule is an example in which the central atom has both shared and unshared electron pairs. The central nitrogen atom in the ammonia molecule has one unshared pair of electrons. VSEPR theory postulates that the lone pair occupies space around the central atom just as the bonding pairs do. This results in the electrons in an ammonia molecule maximizing their separation by taking on the four corners of a tetrahedron. A water molecule has two unshared pairs of electrons. Thus, it is an AB2E to molecule. The oxygen atom is at the center of the tetrahedron. Two corners are occupied by hydrogen atoms, and other corners are occupied by the unshared electron pairs. According to VSEPR theory, the lone pairs occupy space around the central atom, but the actual shape of the molecule is determined by the positions of the atoms only. The bond angles of the hydrogen atoms are 107 degrees in an ammonia molecule, while the bond angles of the hydrogen atoms of the water molecule are 105 degrees. Finally, in VSEPR theory, double and triple bonds are treated in the same way as single bonds. Polyatomic ions are treated similarly to molecules as well. Even though VSEPR theory is useful for explaining molecular shapes, it does not reveal the relationship between molecular geometry and the orbitals occupied by its bonding electrons. To explain this aspect of chemical bonding, chemists use a different model. This model, known as hybridization, is the mixing of two or more atomic orbitals of similar energies on the same atom to produce new hybrid atomic orbitals of equal energies. Hybrid orbitals are orbitals of equal energy produced by the combination of two or more orbitals on the same atom. The number of hybrid orbitals produced equals the number of orbitals that have combined. Weak forces exist between molecules. These forces of attraction between molecules are known as intermolecular forces. Even though these forces vary in strength, they are generally weaker than ionic bonds, covalent bonds, and metallic bonds. Polar molecules contain the strongest intermolecular forces. These molecules act as tiny dipoles as a result of their uneven distribution of charge. A dipole is created by equal but opposite charges that are separated by a short distance. A dipole is represented by an arrow with a head pointing toward a negative pole and a crossed tail positioned at the positive pole. The forces of attraction between nonpolar molecules are known as dipole-dipole forces. These are short-range forces as they act only between nearby molecules. The polarity of diatomic molecules is determined by just one bond. The polarity of polyatomic molecules is determined by the polarity and orientation of each bond. A polar molecule can induce a dipole in a nonpolar molecule by temporarily attracting its electrons, resulting in a short-range intermolecular force. The intermolecular force in which a hydrogen atom that is bonded to a highly electronegative atom is attracted to an unshared pair of electrons of an electronegative atom in a nearby molecule is known as hydrogen bonding. Hydrogen bonding is responsible for the unusually high boiling points of some hydrogen-containing compounds. Even noble gas atoms contain weak intermolecular forces. The intermolecular attractions resulting from the constant motion of electrons and the creation of instantaneous dipoles are called London dispersion forces. Even London dispersion forces act between all atoms and molecules. They are the only intermolecular forces acting among noble gas atoms and nonpolar molecules. London dispersion forces increase as molar or atomic mass increases, since they are dependent on the motion of electrons.